Okay, Chapter 10, Chemical Quantities. 10.1, the mole, a measurement of matter. To start with chemical measurements, we have to use atomic masses. The atomic mass is the mass of an atom in atomic mass units, which we call AMU, or just U, and that is 1/12 the mass of a carbon-12 atom. A carbon-12 atom consists of 6 protons and 6 neutrons, and since that's where all of the mass comes from, or 99.9999% of the mass comes from, they just took the 6 and 6, cut it into 12 pieces, and said 1/12 of the carbon-12 atom is 1 AMU. We're going to round all of our atomic masses to 1 decimal place. So you can look at the 2 examples on the slide. You see number 48, cadmium, has a mass of 112.411. Number 83, bismuth, has a mass of 208.98038. Well, that's a lot of decimal places and a lot of keying into a calculator. So we're just, to make things simpler, we're going to round all our atomic masses to 1 decimal place. So cadmium becomes 112.4 AMU and bismuth becomes 209.0 AMU, because if you look at the digit after the 9, it's an 8, which makes it round up. Now, atomic mass is simple. It's just the mass straight off the periodic table. But what happens if we have a compound, which we have a formula for? If we want the formula mass, it's the sum of all the masses of all the atoms in that compound. The example you see is CCl4, carbon tetrachloride. Carbon tetrachloride is made up of 1 atom of carbon and 4 atoms of chlorine. So if we want to get the total mass of the compound, we take 1 atom of carbon times 12.0 AMU per atom, comes out to 12.0 AMU. And then we add to that 4 atoms of chlorine times 35.5 AMU per atom of chlorine, which comes out to 142.0. When I add 12 plus 142, I get the molecular mass of CCl4 to be 154.0 atomic mass units. Now, when we're talking about formula masses or atomic masses, we're dealing with particles. We call these representative particles, or RPs. A particle would be an atom, an ion, or a molecule, or a formula unit. So below we see examples of each. Most elements exist as atoms, like iron, gold, sodium, mercury. 7 elements consist as diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They're all sub-2s. So then we have molecular compounds, which exist as molecules. Water and carbon dioxide are examples, and ionic compounds exist as formula units: sodium chloride and silver chloride. A mole of any element is the number of atoms of that element equal to the number of atoms. That's exactly 12.0 grams of carbon-12. A mole, by representation, is equal to 6.02 times 10 to the 23rd particles. We call this Avogadro's number. The mole shows the relationship between the atomic mass unit and grams. The mass in grams of 1 mole of a substance is numerically equal to the atomic mass or formula mass in AMU. The molar mass is the mass in grams of 1 mole of that substance. Mole relationships. How many atoms are in a molecule of ammonia? Well, there's the formula, NH3. It's 4 total atoms, 3 hydrogen and 1 nitrogen. 1 mole of ammonia has 1 mole of molecules. How many moles of atoms are in a mole of ammonia? Since there's 4 atoms in 1 molecule, there's 4 moles in 1 mole of ammonia. That would be 3 moles of hydrogen and 1 mole of nitrogen. This relationship would work for ionic compounds broken into its ions, or atoms that make up the ions. Now, this picture is in the bottom right corner of your periodic table. These are the mole ratios that we can use to go from one unit to the next. The molar volume of a gas is 22.4 liters. So at the top you see 22.4 liters of gas at STP, which is 0 degrees Celsius in 1 atmosphere, is equal to a mole of gas at STP. So I can make 2 conversion factors, one with the liters on the top, the other with the moles on the top. We can also say that the mole of any substance is equal to its molar mass. So if we know the molar mass of that substance, which we would have to calculate from its formula, we can then use that to do either 1 mole of that over its molar mass or its molar mass over 1 mole. The last one is Avogadro's number, which is for particles. That's for atoms, ions, molecules, formula units. And there's a mole of that equal to Avogadro's number of 6.02 times 10 to the 23rd representative particles. Since they're equal, you can then make 2 conversion factors out of those. Now, if you're using a Texas Instrument calculator, a TI-30X2S, if you want to enter Avogadro's number, 6.02 times 10 to the 23rd, you would key in 6.02. Then the upper left-hand corner, you'd have to hit the second function, followed by x to the minus 23. Now, x to the minus 1 just is the formula for an inverse, but for a TI, they use the secondary function being the EE, which is an exponent. If we were doing a negative exponent using the same calculator, we would have to do 1.11 second x to the negative first. Then in the bottom right-hand corner next to the decimal is the minus, and that would be minus 5. Don't use the minus in subtraction. You have to use the minus in the parentheses. The second x to the minus 1 is equal to EE, which we call exponential notation. Now, I find a Casio calculator is much easier to use because you don't have to hit the second function and x to the minus 1. A scientific calculator in Casio, if you look what's circled, they have an EXP button. That's the exponent button. So if I were going to put in Avogadro's number, I would hit 6.02, then I hit the exponent, which is right next to the decimal, and then 23. Notice I do not hit times 10. All you're doing is you're hitting the exponent button, which is equal to times 10 to whatever power. And if you were doing a negative exponent, like 1.11 times 10 to the negative fifth, you would put in 1.11 exponent, and then above the 7, 2 up, is a minus sign in parentheses, very much like on a TI calculator. So you would hit exponent, negative 5, and then if you hit the equal sign, it will show you on the screen that you inputted it correctly. Now, how to set up a word problem for conversions. When we set up word problems, very much like the videos that you were viewing, what you're going to do for this is we're going to use this system of what we want and what we have. So you kind of have to read through the problem and figure out what information is important. So I have an example for you here. Magnesium is a light metal that is used in manufacturing of aircraft, automobile wheels, and tools. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? So when I set up my problems, the first thing I will do, if you look outside of the, underneath the red box, you read the problem, figure out what you want. That's your W. And notice in the box, I want moles, because whatever unit is written in the problem that does not have a number with it is what you're trying to get to. That's what you want. The 1.25 times 10 to the 23rd atoms is what I have. So you'll notice up in the red box, I have W dash moles, mg, and H dash 125 times 10 to the 23rd atoms. So that's my have and my want. The reason we do this, you're going to see shortly. What you want is the unit without the number, and what you have is the unit with the number. All numbers need units. So we set up as follows. We put W dash H dash. We write the unit you want after the W and the given number and the unit after the H. Doing this is going to set up your conversion factor. Write what you have followed by the multiplication sign. So you look up there right in the middle, 1.25 times 10 to the 23rd atoms magnesium, multiplication sign, and now I'm going to use my conversion factor. Well, my conversion factor, what I want is moles. So 1 mole is going to go on top. When we're doing problems in this chapter, it's always going to be 1 mole. Now, when we get to stoichiometry and going from different things, it may not be 1 mole. But on the bottom, to get rid of my atoms, I'm going to use Avogadro's number, because Avogadro's number is in particles. So you'll notice in my numerator, I have 6.02 times 10 to the 23rd RP. Well, RP is the abbreviation for atoms, ions, molecules, form the units. It's just a basic substitution. So then I do the math. I do 1.25 times 10 to the 23rd times 1, and I divide by Avogadro's number of 6.02 times 10 to the 23rd, and if I did it correctly, I get my answer of 0.208 moles. Now, the first worksheet is we're going to just talk about the mole and how it's related to Avogadro's number. So a mole is equal to 6.02 times 10 to the 23rd representative particles. From this equality, you can get two conversion factors, as I've already stated. You could have 1 mole in the numerator and Avogadro's number in the denominator, and you can have Avogadro's number in the numerator and 1 mole in the denominator. We can use either of these conversion factors to convert from either moles to representative particles or vice versa. So the first one is the one that we just did, converting representative particles to moles. We had 1.25 times 10 to the 23rd atoms. We wanted to know how many moles that's equal to. So we put what we have in the front, then we multiply by 1 mole on the top and Avogadro's number on the bottom, and we get the 0.208. So let's try a different problem. How many moles is 2.80 times 10 to the 23rd atoms of silicon? So now we have a different element and we have a different amount. So you look at my problem setup. I have 1 mole of silicon on the top and 2.8 times 10 to the 23rd atoms as my half. So I'm going to set up the problem like this. I always put what I have out in front of the problem because that's what I'm trying to convert from. The next thing I want to do is put my multiplication sign and my conversion bar. And in my conversion bar on the bottom, I'm going to put Avogadro's number because it has the same units, atoms. So by putting it in the denominator, it allows me to cancel atoms. And then I want moles, and we know that Avogadro's number is equal to 1 mole of anything. So I put 1 mole on the top. So doing the math is identical to the one we just did. The only difference is I changed what we had to a different number. So I do the math, I plug it into my calculator, and I get 0.465 moles of silicon. Same setup, same problem, different starting point, different ending point. How many moles is 2.17 times 10 to the 23rd molecules of bromine? So this one's only different because it's molecules versus atoms. So I put my 1 on the top, I want moles. I put my half on the bottom, 2.17 times 10 to the 23rd. Well, I start out with what I have. I'm then going to put my multiplication sign, my conversion bar. On the bottom of my conversion bar, I'm putting the unit that cancels. And the unit that cancels is Avogadro's number cancels molecules. And since I want moles on the top, I put 1 mole on the top. So now, same math, different numbers, same process. And when I get my final answer, I get 0.360 moles of bromine. Now I'm hoping that as you're doing these, you're actually writing them in and calculating them and pausing the video while you calculate it, because you get a lot more out and you'll be able to see if you're doing things properly or not. So now, instead of going from moles, or 2 moles from molecules, now we want to go the other way. So to convert moles to atoms in a compound, this is a little bit different. This is a little more steps to it. Propane, C3H8, is a gas used for cooking and heating. How many total atoms are there in 2.12 moles of propane? So I want total atoms, and this time I have moles. So I write my W, I write my H, and then you can see how this one's a little bit different. I have it all set up and done for you. I start with my 2.12 moles of C3H8 propane. This time I multiply by Avogadro's number per mole, so the moles cancel. Well, that gives me not atoms, but it's giving me a molecule because C3H8 is a molecule. So I have one more step to do. There are 11 atoms, 3 carbon and 8 hydrogens in a molecule of C3H8. So I'm going to multiply the total atoms over 1 molecule. Now notice I don't write molecule, it just takes up too much space. So I just substituted RP. So now I do my step. Moles times Avogadro's number times 11. And I get 1.40 times 10 to the 25th atoms just by canceling my units. So I'm going to do one more. I want to know how many atoms are in 1 mole of sulfur trioxide. So I want total atoms. I have 1.14 moles. So step by step, I put 1.14 moles of SO3 in the front. I'm then going to multiply by something over 1 mole because I want to cancel the moles. So the first thing and always thing is to remember is whatever you start with on the left, the next place it's going to end up on the bottom in the denominator to cancel those units. So we want to get to atoms, so we have to go through Avogadro's number. Well, Avogadro's number is in molecules because SO3 is a molecule. So I have 6.02 times 10 to the 23rd molecules. But I don't want molecules, I want atoms. So I have to look at my compound and see what are my total S and O. I have 1 S and 3 O's. Well, that's 4 atoms. So I put 1 molecule on the bottom, and there's 4 atoms per molecule. So this way, as I do my math, my moles cancel, my molecules cancel, and I'm left with atoms. So when I do the math, I put in 1.14 times 6.02 times 10 to the 23rd times 4, all divided by 1. And I get 2.75 times 10 to the 24th total atoms. Now, number 4 is similar to the one up top, except I want to just do one thing. Now, this one's a little different from the one above. How many carbon atoms are in 2.12 moles of C3H8? How many hydrogen atoms are in 2.12 moles of C3H8? So this is similar to the one up top, above 3, but it's a little bit different. So watch how I do this. I start by putting my 2.12 moles in the front. Now I want to get rid of those moles, so the next step, I'm going to put 1 mole on the bottom, and since I'm trying to get to atoms, I have to go through the formula of C3H8, which is a molecule. So I use Avogadro's number to get rid of the moles and turn them into molecules. But I don't want molecules, I want atoms. So on the bottom, I'm going to put 1 molecule, and on the top, I'm going to put 3 carbon atoms, because this time I don't want the total, I just want the part. So then I do the math, 2.12 times Avogadro's number times 3, all divided by 1, and I get 3.83 times 10 to the 24th atoms. So I want to do this again for hydrogen. So I'm going to have my same starting 2.12 moles. I'm going to cancel those again with 1 mole of C3H8. The second step is going to be identical to the one we just did, Avogadro's number on the top. That gives me molecules. But I don't want molecules, I want hydrogen atoms. So I'm going to put 1 molecule on the bottom, and how many atoms there are? 8. So when I do this math, and I get it, I get 1.02 times 10 to the 25th. Now, what I want you to do for me is I want you to take the 2 numbers for number 4 and add them together. So 3.83 times 10 to the 24th, add it to 1.02 times 10 to the 25th. And when you do that, you'll notice that the total is the same as you got above doing it as one problem. Because think about it, if 11 atoms total makes the 1.40 times 10 to the 21st, 3 atoms plus 8 atoms equals 11 atoms. So yes, you will get the same thing. Now, because of decimal places, it won't be identical, but when you round it, it will still be the same. Finding the molar mass of a compound. As you've seen before, to get the molar mass of a compound, what you need is each of the individual atoms and how many there are and the total there are. So we're going to do this the right way up front, and then after we do this, you don't have to show me the work, but for now I want you to see exactly how we're getting the answer, so it's not just some magical number. So the first thing is we want M, which is the molar mass of hydrogen peroxide, H2O2. Now, the only halves I have are the masses from the periodic table. The mass of 1 mole of hydrogen is 1.0 grams. The mass of 1 mole of oxygen is 16.0 grams. So then what I'm doing is the subscripts are now my moles. So in the formula H2O2, I have 2 moles of H. So I multiply that by 1 gram per 1 mole. That gives me 2 grams of H. I then do 2 moles of O times 16.0 grams of O per mole, which gives me 32.0 grams of O. And then when I take the total, my 2.0 plus 32.0, it gives me a total mass of 34.0 grams of H2O2. Now, numbers 5 and 6 are tricky only in the fact that you're not given the formula. In the first one, you were given the formula. So what you have to do is you have to delve back into your formula writing abilities and write the proper formula. So I want the molar mass of phosphorus trichloride. Well, the fact that there's a prefix tells me that's a molecular compound. So the fact that that's a molecular compound, I then just put the P, I put the Cl, and I put the 3 behind it to give me PCl3. I also want to do it for 1 mole of sodium hydrogen carbonate. So then I go back into and realize that sodium hydrogen carbonate that has a polyatomic must be ionic. Sodium is +1, hydrogen carbonate's -1. So I get NaHCO3, which I'm now going to break down into 1 mole of sodium, 1 mole of hydrogen, 1 mole of carbon, and 3 moles of oxygen. And then to get my molar masses for each of these, what I need to do is look up each of the elements' atomic mass on the periodic table, which is numerically equal to their molar mass. So I look at my periodic table and I see for P, it's 31.0. I see for Cl, it's 35.5. So you'll notice in my calculation, I have 31.0 grams of P plus 3 times 35.5, which is 106.5 grams for Cl. I add those two together, I get 137.5 grams. For sodium chloride, I have 1 mole of sodium, so I need the molar mass of Na. I have 1 mole of H, so I need the molar mass of H. I have 1 mole of C, so I need the molar mass of C. And I have 3 moles of O, so I need 3 times the molar mass of O. And when I do that, sodium is 23.0, hydrogen is 1.0, carbon is 12.0, and 3 times 16 is 48.0. Altogether, that equals 84.0 grams of sodium hydrogen carbonate, or sodium bicarbonate, or baking soda.
The mole is an especially useful tool for chemists because it allows them to express the number of representative particles of a substance in grams. For example, a mole of carbon atoms has a mass of 12 grams. Huh? My brain hurts.
Ciao, signorina. I understand that you're having a little trouble understanding the mole.
Who are you? Why are you in my room? And why are you dressed so funny?
Actually, you're in my room. You've traveled back 200 years. This is my office in this high school in Turin, Italy.
I must not be drinking enough water after I run. Maybe I'm dehydrated, delirious.
You're not delirious. You're just dreaming. It happens all the time. So, tell me, what kind of problems are you having understanding the mole?
Okay, just go with the flow here. Eventually I'll wake up and everything will be back to normal, right? How can you help me understand the mole?
I am none other than Count Lorenzo Romano Amadeo Carlo Avogadro. You know, the lawyer turned scientist who determined that equal volumes of gases contain equal numbers of particles. Actually, it's a good thing that the Frenchman Joseph Louis Gay-Lussac had already published his law combining volumes. That's what helped me determine my gas law. That's named after me, you know. Avogadro's hypothesis.
Wait a minute. I thought you had different facial hair. And I thought Avogadro had something to do with some number. Wait, That's it. Yeah, that's right. Some really big number. I remember 6.02 times 10 to the 23rd. Avogadro's number.
Yes, well, first of all, I just went cycling in Spain. This is all the rage. And actually, some other guy is going to figure that number out 50 years from now. But he's going to name it in honor of me, too.
That's pretty cool, but so what?
Well, that number is the amount of particles in 1 mole of something, usually atoms or molecules. Oh, like the dozen eggs you bought. How many eggs are in that dozen?
12?
So, a dozen eggs contains 12 eggs. A mole of an element like carbon contains 6.02 times 10 to the 23rd atoms of carbon. The mole of a compound like carbon monoxide contains 6.02 times 10 to the 23rd molecules of carbon monoxide.
So what?
So what? So, now that you know that every mole contains the same number of particles, you can calculate the mass of a mole in any element or any compound. Again, take carbon for example. A mole of carbon has a mass of 12 grams. How do you get that mass? By converting the atomic mass of carbon, 12 AMU, to grams. The mass of a mole of an element or compound is called its molar mass. For compounds, you can calculate molar mass from the atomic masses of the elements in the compound. For example, what's the atomic mass of oxygen? 16 AMU. So, what's the molar mass of carbon monoxide?
28? And so that's 1 mole of carbon monoxide, right?
Esattamente, signorina.
Hey, I think I get it. So if you know about the mole, you can predict what will happen in a reaction. That means you will know how much carbon monoxide you get if you combine, say, 2 moles of carbon with 1 mole of oxygen molecules. 56 grams. 56 grams. Cha-ching.
So what?
So that would be totally important. Like if you had to make a certain amount of something, you could calculate the total amount of raw materials you needed.
Esattamente.
Okay. I gotta wake up now so I can finish my homework. Wake up.
And don't forget, non fermate mai esplorare vostro mondo.
Now, this is me back in 1995. As you see on the board, I was doing the same thing we're doing now. This one actually is I believe it's a volume 2 gram problem, but moles have not changed in the 25 years between 1995 and now. So the way that I'm teaching it has not changed either. Now, the last thing we're going to do in this section is they're showing you, once again, what I've shown you is how to calculate the molar mass. So people that are getting it, you know, for Ga2H6, you need 2 Gas plus 6 H's, get their masses, and add them together. But this is showing you mathematically how it is 145.4. If you're having some problems, look over this test right here, look at this example, and see if you can follow it. Now, carbon dioxide, 1 carbon, 2 oxygens. So I'm going to do 1 mole of carbon times 12.0 grams, which is 12.0 grams of carbon. 2 moles of oxygen times 16.0 grams per mole is 32.0 grams. 12 plus 32 is 44. Mercury 1 fluoride, Hg2F2. So 2 moles of Hg times 200.6 grams per mole is 41.2. 2 moles of F times 19.0 grams per mole is 38.0. 401.2 plus 38.0 is 439.2 grams. Magnesium thiotellurite, 3 magnesium moles. So 3 times 24.3 is 72.9. 1 mole of tellurium, 127.6. 5 moles of sulfur, which is equal to 5 times 32.1, or 160.5. I add the 3 together, 72.9 plus 127.6 plus 160.5 equals a total mass of 361.0 grams of Mg3TeS5. Now this next one is different. We haven't seen this yet with any of our formulas, but this one has parentheses. And now I'm going to show you the reason we needed the parentheses in copper 2 cyanide was to show there were 2 cyanides. But when you're doing molar masses, that's also important where that 2 is and where the parentheses go. So this time I have 1 mole of copper, which is 63.5 grams per mole, which comes out to 63.5 grams of copper. I have 2 moles of cyanide. Well, cyanide is Cn, so I have 2 Cs and 2 Ns. So you'll see in my calculations, I do 2 moles of C times 12.0 grams per mole, which is 24.0 grams. I have 2 moles of N times 14.0 grams per mole, which is 28.0 grams. And then I add the 3 together, 63.5 plus 24.0 plus 28.0 comes out to 115.5 grams. So you'll notice that the parentheses and the 2 only goes to carbon and nitrogen, not to copper. So that's the reason why we used them originally, and when you're calculating masses, that will also come in fact.